Welcome back. In the second half of the chapter, we will talk about the other non-volatile memory that is designed to store data, the integrated EEPROM. The ATmega 328P has 1 kilobyte of it. In average, every byte can survive a rewriting of about 100,000 times, which is 10 times more compared to the flash memory. In addition, it has a byte-wise access. That means every address is addressing one byte instead of an entire word like in the flash. The EEPROM is not organized in pages, and therefore an update does not require the entire page to be rewritten. So it is a lot easier to handle. But let's have a look. There are a few registers which access the EEPROM. First, we have the address register, which contains the address that the software developer wants to read from or write to. Since the EEPROM has 1024 bytes, we need 10 bits to address all bytes. Please note that there is a small mistake here in the datasheet. The EEAR9 can be read as well as written to, so this should be R and W, and the initial value is unknown. Then there is the data register, which contains the byte to be written or the byte that has been read from the EEPROM. And the last register for the EEPROM is the control register, which tells the EEPROM what the software developer intends to do. The EEPM1 and 0 bits determine what the write operation should be. We have the erase and write operation that is atomic, which means that it is a single operation that cannot be interrupted once issued. Or we can only write or only erase. Then there is the EERE, which is the EEPROM ready interrupt enable. For instance, data can be sent to the EEPROM and the program can do something else while the data is written. An interrupt request is issued once the write is complete. The writing to the EEPROM is comparatively slow, hence it is a good idea to utilize this functionality. Then there is the EEMPE, which is EEPROM Master Program Enable. Often in literature it is also called EEMWE for EEPROM Master Write Enable. The EEPROM is secured against overwriting data accidentally, and in combination with EEPE or EEWE, the data is committed to the EEPROM. We will see in a minute how that works. The EEWE bit can be polled to check if the previous write completed and the EEPROM is ready again. And lastly, there is the EERE, which strokes the EEPROM to read data from the desired address and stores it in the data register. To write a byte to the EEPROM, the following sequence is to be followed to ensure success. First, the software developer has to ensure that there is no write going on currently, and in a second step, no write to the flash is executed at the same time. Then the address and the data are loaded in any sequence. After that is completed, the data in EEDR needs to be written at the address in EEAR. For that, first the EEMPE bit is to be set, while the EEPE bit is to be cleared. Within 4 clock cycles, the EEPE needs to be set. If between these two commands are more than 4 clock cycles, the data is not written to the EEPROM at all. Fortunately, there are helper functions provided by the AVR library which take care of that sequence. Here we see an example utilizing the functionality to write to the EEPROM provided by the AVR library. The entire sequence that we had in the earlier session is hidden in the EEPROM write byte function call. The same address is read again from the EEPROM and stored in EE_data. There are many functions available depending on the data type and operation to perform. There is the read, write and update as operation. The update functionality is quite useful as it only writes a byte to the EEPROM if the data at that location differs from the data to be written. Only if that is the case, the data is written. It helps in preserving the limited amount of write cycles that the EEPROM can sustain. However, 100,000 cycles per byte is still quite a lot. As type, there are byte that are 8-bit, word with 16-bit and double word consisting of 32-bit available. Also, floating points can be handled or entire EEPROM blocks can be read and written to comfortably. Each of the functions checks if the EEPROM is ready to perform the desired operation. If not, the program waits till it is ready. If data is written, then the global interrupts are disabled while the operation is performed. At the end, the global interrupts are restored if they were enabled at the beginning. As you can see, the operations are performed based on polling of the respective status bits. Let's see if that is a good idea. This table summarizes the typical time requirements for each of the operations. If an erase and write operation is to be performed, it takes 2.4 milliseconds. That means using the AVR helper functions, for 3.4 milliseconds nothing happens while the EEPROM is written. Since global interrupts are disabled during that time, the CPU does not even react to data that is received through UART, for instance. That time requirement is quite substantially. Therefore, it is a good idea to use interrupts. The software developer can commit the data write and then let the CPU do something else, such as waiting for the next byte to be received from the UART interface or just sleep. Once the EEPROM is ready again, the interrupt request is used, and in that ISR the next byte can be loaded to the data register in case multiple bytes are to be stored in the EEPROM. What do you need to do if you need to initialize the EEPROM with some fixed values for instance, configuration purposes? Here is our program once again. To pre-store variables and their values in the EEPROM prior to the program execution, two options are available. The first option is achieved in the program itself. There is a global type which is stored in the EEPROM as indicated by the EEMEM keyword. This keyword ensures that the compiler knows that this variable is not in the data memory or SRAM, but in the EEPROM. The disadvantage of this method is that with every reset the data is to be written, and we have to keep in mind that 1. The number of write cycles is limited, and 2. It is very slow. Better would be the EEPROM update byte function instead, which at least checks if the data has been written to the address 100 before. The alternative and second option to that is to directly initialize the value as shown for the variable data_word. The compiler is then able to store those initialization values to a separate file, which then can be used to write the values to the EEPROM while writing the program to the flash memory. So no write or update functions within the program itself are required in that case. In addition, imagine the configuration is to be changed or updated. For the data_byte, I need another byte in the EEPROM that tells me if the data stored at data_byte is valid or not. Only if the data is not valid, it should be initialized with 100. For the variable data_word, this check is not required, since the variable is only overwritten if another EEPROM file is supplied and uploaded. We will see in the next session how that works. It becomes much clearer there. So let's dive in. The programs of this session are stored in cores, memory, and EEPROM in the VirtualBox image, or also attached to the resources folder of this lecture. Okay, I'm in cores, memory, EEPROM, and EEPROM init, and here I have a little program. Let me show you the content of that program. I have an 8-bit unsigned integer variable that is stored in the EEPROM called data_byte, and a data word of 16-bit unsigned integer, and it is already initialized with 1, 2, 3, 4 in hexadecimal format. Then I write 100 to the address where data_byte is located in the EEPROM, and I read the word 1, 2, 3, 4 and stored in E_data. And then I have a simple check. If E_data is equal to 1, 2, 3, 4, that means this read was successful, then turn on the onboard LED. After that, sit in that while loop and don't do anything anymore. Okay, let's compile this. And we see here that the AVR size tool gives us an EEPROM entry of 3 bytes. This is 1 byte for the 8-bit unsigned integer and 2 bytes for the 16-bit unsigned integer, in total 3 bytes. However, if I want to upload this, then an error occurs. Problem is that this address is out of the range. What AVR-dude tries to do is it uploads the entire hex file into the flash memory, although some part needs to be stored in the EEPROM, and AVR-dude is not aware of this. That means we have to separate out the EEPROM section from the program section, and to do so we can use AVR object copy Let's have a look at some parameters. So I typed in -h for help, and fortunately there is a parameter that says remove section and then the name. And we have already a name, and that is this one, the EEPROM. That means I use AVR object copy in Intel hex format, remove all sections by this name. What's my input? It's the EEPROM init.elf that contains both the program plus the EEPROM, and I stored in that hex file. And now what I need is I need only the EEPROM section. So I have to create a file that contains only the EEPROM section without the program section or data section. And let's see again if there's a parameter. Unfortunately there is one, -j. It says here only section, only copy section name into the output. That's perfect. So again AVR object copy -o I hex -j. I would like to have only this section, and from this file, and I store it into EEP. Okay, here this contains only my program, and this contains only my content for the EEPROM. However, there's one more problem, and that is this address. This address is still active, and we can have a look at this, namely with AVR object dump -x, that means show all sections, EEP. And here's this local memory address, but the EEPROM has only 1024 cells. That means this address is way too high. So I have to realign the entire content of this EEPROM to the address 0, because the address 0 of the EEPROM is the very first byte of that EEPROM. And again, object copy will help me of doing so. There's a parameter called change section local memory address. Then I have to add the name, then an equal sign or plus and minus if I use the relative addressing, and the value. Okay, so let's try that. So let me add this parameter. That is change section LMA, then the section name. I have only one, and that is the EEPROM section, and I would like to put it at address 0. Let's analyze the file, and you see that the local memory address has been set to 0. Alright, let's upload this program. And for that I just copy the avr-dude command that we used earlier in the makefile. This is my program file that I created right here without the EEPROM section. But I also have to upload the EEPROM section. So I add another -u, EEPROM. I would like to write to it, and what is the content? EEPROM init.eep. This writes to the flash, this writes to the EEPROM, this file. Perfect. If you do not want to rewrite the EEPROM, for instance, this is just configuration data, so it doesn't need to be rewritten every time you found a bug in your program and you upload a new program into the flash, you just remove this parameter. If you want to reinitialize the EEPROM only without overwriting the flash, you can remove this parameter. Let's see what happens. And we will see that 234 bytes of flash has been written and verified, and then 3 bytes of EEPROM have been written and 3 bytes have been verified. Now let's have a look at the content of that EEPROM. And for that I can use AVR-dude. I don't want to download the flash, but I would like to read the EEPROM. And let me store it in another file, and that is downloaded EEPROM.eep. It takes a little bit of time. It's only 57,600 baud and it's 1 kilobyte. And here we are. This is my EEPROM, 1024 byte. Obviously I would like to have a look at the file. For that you can use any hex editor. For instance, there is one in the file manager Midnight Commander. Just go down and then press F3 for view, and this is a text view, and you can see down here it's hexadecimal. And you see that there are lots of F's and there are some zeros here. Probably something has been saved earlier at these locations in some other project. And here we see 1, 2, 3, 4, and 64 is just uninitialized memory. This is our 16-bit value and this is our 8-bit value. With a click on quit, you exit this, and you can also exit this Midnight Commander. All these commands are also here in that makefile _EEPROM, so you don't have to manually write down these commands. And to use it, you can use make -f makefile EEPROM with the target that you would like to build. Okay, that concludes the session about the EEPROM, and we will return to the lecture. See you in a bit, and thanks for watching. What did we do in this chapter? In the first half, we talked about the flash and figured out that the flash is quite easy to read from and useful to store constants containing large values with a high memory footprint. However, storing data into the flash while the program executes is an entirely different story. First, the flash can be locked to protect it against modifications. The issue is that the flash is shared between the program that is executed and the data to be stored. Hence, we have to make sure that we do not overwrite the user program unintentionally. In addition, the flash is organized in pages, and even just a byte to change requires the entire page to be erased first. And last but not least, there are two different sections in the flash, the no read while write and read while write section. Only if the no read while write section is executed, the read while write section can be written to. On the other hand, EEPROM is quite easy to handle. In case a read from the EEPROM is required, the address is stored in the address register and the EEPROM is strobed. The data then can be picked up from its data register. Similar, the write sequence. The only difference is that the data is to be stored first in the data register and then the EEPROM is strobed. And what is next? The next chapter is going to be interesting. We extract the ATmega from the Arduino board and let it run solo. What are the advantages and the disadvantages of doing so? But before going there, please have a look at the exercises. The earlier one about the flash and the one at the end of this chapter about the EEPROM. After you enjoy them, I will see you again in the next chapter. Thanks for watching.